Chapter 20, Lesson 4. In the previous short lesson we talked about the setup of the voltaic cell, and essentially that's a battery. We said there's an anode compartment and a cathode compartment. Reduction happens at the cathode and oxidation at the anode. And when oxidation happens, electrons are released. So after the electrons are released, they flow through an external circuit toward the cathode, and then you can hook up any device that needs the electricity and make it work. Now I'm going to take a look at some math behind this idea, and these will be called cell potentials. And the analogy we'll make is think of the water flowing down a waterfall as releasing energy. So we can, for example, harness the falling of the water. We can set up some sort of turbine down here that collects this energy, like a windmill, or not a windmill, I'm sorry, a water mill of sorts. And likewise, we can do the same thing with our battery, our electrons. So this is actually an analogy, even though different forces are involved. What we're doing is we're flowing from a higher to a lower potential energy in both the waterfall and also in a battery, and that's what we call these cell potentials. The word cell actually refers to the half cells, the oxidation and the reduction half cells. So this force that makes it flow, in the case of waterfall, it's gravity. In our case, it's called the electromotive force, or EMF for short. It's also called the cell potential, and it's designated as E sub cell. So this is going to be the electromotive force, or the cell potential. Usually we'll refer to it as the potential. And the units of the cell potential is or are volts. Now you may have heard of volts before, but let's define volts, as we'll be using volts throughout this chapter. A volt is actually a joule per coulomb. Now coulomb is a unit of charge, and a joule is a unit of energy, if you recall. So this is actually, volts represent energy, but they represent an energy per charge. So really what we're talking about here is the potential for the energy being released from the reaction. So these are the breakdown. This is the breakdown, joule per coulomb. We'll talk mostly about volts, but this definition will be important later on to us. Now, many of these reduction potentials, or these voltages, have been measured and tabulated, and usually they're listed. In fact, in the back of our book, in Appendix E of our textbook, we have a whole few pages, actually a whole page, probably one page, of all these potentials, these voltages for the various reactions that we know about, the most common, you can say. So here it's reproduced in part. So for example, we are given a half reaction. Now these are broken down into half reactions. For example, you can see the silver, when silver plus becomes silver as it's getting reduced, the voltage for that is 0.80 volts. Now these are called reduction half reactions. So these are called reduction potentials, because we're listing every reaction here as a reduction reaction. In other words, everything is being reduced here, and they're ordered to put the guys at the very top as having the highest potential. Highest potential for reduction. We could have listed this with oxidation potentials, but this is how it was customarily set up. So this is the highest potential for reduction at the top. And actually you can say that at the bottom we have the opposite, oxidation potential. So this is called a reduction potential stable. And you'll notice that at the very top, you'll notice the species is fluorine. Now what we know about fluorine is that fluorine is extremely electronegative, the most electronegative of all the elements, which means it really desires electrons. And fluorine actually sits at the top of your reduction potential stable, because fluorine has the highest desire, you can say, for being reduced. That's why it's at the very top. Its reduction potential is set up as 2.87. And then everything down here, if you take a look at lithium, lithium is at the bottom. We know that lithium does not exist on Earth as a as a pure metal, it always exists as an ion because it's so reactive. Lithium, being from the first group, does not want to get reduced. It really wants to get oxidized. And that's why lithium is extremely reactive. If you throw lithium in water, we know that lithium placed into water gives you a pretty fantastic reaction, and so does sodium right above it. And you get yourself lithium hydroxide and hydrogen gas produced from water. It'll react with water itself. And lithium in this case will get oxidized. So lithium really wants to get oxidized. It does not want to get reduced. In fact, its reduction potential is negative. And this tells you that lithium does not want to get reduced. Does not want to reduce. And that's why it's at the very bottom of your reduction potentials. So we are actually going to be using these reduction potentials to do some calculations. So this is kind of an explanation of the same thing. Again, at the top you have the reaction listed with the highest reduction potential, and at the bottom the opposite. And by the way, these are the opposite. This table is actually the opposite of the activity series. We've seen the activity series in chapter 4. And remember, your most active metals like lithium, like sodium, are at the top of the activity series because they are so active. Here, they are actually at the bottom. So this is like a flipped version of the activity series. The activity series, you can say, is an oxidation potential because at the top we list metals that really want to get oxidized because they're so reactive. Now all this is actually based on, if you're wondering, well, why, for example, is fluorine 2.87 or 2.67? How did we figure those out? Well, we all based it on hydrogen. We've decided for hydrogen to have a value of 0, and then we derived the reduction potential of every other reaction from hydrogen. This is kind of like doing setting the density of water being 1, and then the density of every other object being higher or lower than that 1. Think of that's analogous. So when we see hydrogen being reduced, hydrogen plus going to hydrogen 0, and it's being reduced, that's why it's accepting electrons. Its voltage is set up as 0, and everything else in regards to that. In fact, if you take a look at the reduction potentials table, here is hydrogen. Here's a reaction that we just saw, and 0 is its reduction potential, and it's defined as 0 because everything is based off of the hydrogen. So what we're going to do now, because all those are half reactions, we're going to combine the half reactions together to give you an overall reaction for the whole entire reaction. And these are going to be called just the overall cell potentials. What we'll have to do is we'll have to take the cathode portion and subtract it from the anode portion. Now remember that the cathode is where reduction happens, and the anode is where oxidation happens. Remember, the vowels are the way to remember, and the constants are the way to remember it. And if you recall, electrons are produced, here's your battery, electrons are produced at the anode, and they travel through an external circuit to the cathode. Because electrons are produced at the anode, that's where oxidation happens. Oxidation is the release of electrons, and so electrons naturally must go toward the other side, toward the cathode side, where reduction takes place. Well, what we're doing in this cell potential equation is think of this as a form of final minus initial. Whoops. Final minus initial. In other words, we're going to do the cathode where the electrons end up minus the anode. So we're backtracking. So this is not really delta E. Delta E is actually something different, but analogous to it, you can see what we mean. So cathode minus anode, final minus initial, and that's the way to remember this reaction. And these numbers are listed in the table. In fact, this red means the reduction potential of the cathode minus the reduction potential of the anode. And these are referring to actual equations. So why don't we take a look at that, what we mean. So for the battery that we've been discussing and looking at, the zinc and copper battery. Zinc's reduction potential is negative 0.76. Copper's reduction potential is positive 0.34. Now, what we do is first, by looking at these two, we can figure out which reaction will end up being reduced. It's the one with the highest reduction potential. So this is reduction because it has a higher reduction potential. That's why we decided that it's going to be the reduction. And the other guy, automatically, it will be the oxidation half. And so we take the reduction potentials and we just plug them into the equation. We do cathode minus anode, final minus initial. Our cathode is 0.34, and that's why we put this number here. And then our anode is negative 0.76. Now it's minus negative 0.76, which ends up being plus, and our overall voltage, our overall cell potential is 1.10 volts. So this is how we would solve for the voltage. And if you take a look at a battery, take a look like at a double A battery, for example, it'll say the voltage, so it'll say 1.5 volts on it. So batteries actually tell you the voltage, which they're actually telling you the difference between the oxidation and the reduction half reactions. And that's how we get, this is the potential energy difference. Now, before we do an example, we have to say something here. Looks like we have a hole. Because cell potential is based on potential energy per unit of charge, it is an intensive property. Intensive. If you recall, intensive properties do not change when the amount of matter present changes. So it is kind of like density. Remember, density is mass over volume, so no matter if you have a small chunk of matter or a big chunk, the density will be the same for both. Well, the cell potential is exactly the same way because you're dividing the two numbers. Yes, your mass goes up, but so does your volume, which cancels out. Same thing here, your joules go up, but so does your charge. Your charge comes from electrons. Electrons. So the more energy you have, the more electrons flow, and the overall voltage doesn't change. This is important because here it says if the coefficients of a chemical reaction double, the voltage stays the same. It will stay the same. This will be different than what we did for delta H and delta S and delta G. Remember these, when we doubled the reaction, these doubled. But here, voltages will not double. And that's, think of it kind of like the voltage doesn't, it just says E cell. It does not have a delta in front of it. So this is, it's different than our deltas. So why don't we do an example? Here it says, using the standard reduction potentials, calculate the voltage, EMF, which just means the voltage, for the voltaic cell based on this reaction. Now, this reaction has been balanced for us, thankfully. And all we have to do is take a look at our reduction potentials table. Now, what we have is we have dichromate becoming chromium 3+. So if we take a look, this is actually our, if we analyze the charge, we'll see that each chromium here has a charge of +6, because you have 7 oxygens, each is -2, that's -14. So this side must be +12. So each chromium must be +6. So what's happening is chromium is undergoing reduction. So this is actually your reduction half reaction. The other half reaction is iodine minus becoming iodine. This is actually your oxidation half reaction. And you can say it's oxidation because iodine is going from a -1 charge to a 0 charge on the iodine here. So it's going up in charge, it's oxidizing. So now that we've got our two reactions, and the rest of it, the water and the hydrogen ion, are actually there to be able to balance. And notice we're balancing this in acidic conditions. So to get the overall voltage for these two half reactions, we apply our equation, which said that the overall cell potential equals the reduction potential of the cathode minus the reduction potential of the anode. Again, think of it as final minus initial. So what we'll do is, remember, reduction happens at the cathode, so we'll take the cathode number, the reduction number, and subtract it from the oxidation number. So why don't we backtrack? This will be a little strange. Go back about 6 slides or so, and let's see if we can find these two. Remember, we're looking for dichromate becoming chromium 3+, and iodine minus becoming iodine. So go and flip back. Clean this up a bit. So here's what we're looking at. The first reaction is actually given to us right here. This is our first reaction. And the voltage is 1.33 for this half reaction. The second reaction is actually given to us right here. Now, if you take a look, this one is higher up, and we said it has a higher reduction potential, so it was actually our cathode. It was already being reduced when we analyzed the equation. So this is our reduction, so this is our cathode, and this is our oxidation, or anode. And this matches up because the higher up you are, the more of a reduction potential you have, the more likely you're going to be reduced. So what we'll be doing is we'll be taking 1.33 minus 0.54. So take those two numbers down. Oops. So we had 1.33 minus 0.54. And if you do this calculation, you should come up with 0.79, if I'm not mistaken. This gives us 0.79 volts. And this is really it. It's actually pretty simple to determine the voltage of the cell. You have to find your reduction half reaction and subtract it from your oxidation half reaction. And it's as simple as that. Why don't we do one more example before we wrap up the lesson. It's a variation of the previous example. And here it says we have a voltaic cell, or a battery. Remember, voltaic cell is really a fancy way of saying a battery, based on the following two half reactions. We have cadmium becoming cadmium 2+ becoming cadmium, and then tin 2+ becoming tin. Now both of these are written as being reduced. Here it says, A, determine the half reaction that occurs at the cathode and that occurs at the anode. Write the overall reaction and determine the overall cell potential. So first what we'll have to do is we'll have to find these two potentials. Let's look up in the table and find the two potentials. We got cadmium 2+ to cadmium, tin 2+ to tin. So flip back to that page. So if you take a look, cadmium is nowhere to be found, and tin is nowhere to be found. At this point you may have the temptation to panic, but not panic. Go to Appendix E. Appendix E will save us from the trouble. So take out your book, and my book has been abandoned, so we'll have to take a look at the we'll have to be back. So give me a second. We'll be right back after these messages. We are back, and Appendix E is in the process of being opened. So take a look at Appendix E, and we should find, let's go ahead and circle back. Oops. So in Appendix E, we find that cadmium has a reduction potential of negative 0.403 volts, and tin has a reduction potential of negative 0.136 volts. Now from this we can actually determine which one will be reduction, because remember, the higher the reduction potential, the more likely it will be reduced. So tin has a higher reduction potential. So tin will actually be reduced. And reduction happens at the cathode, therefore the cathode is the tin. And then the opposite guy will be the anode. So the anode will be cadmium. And again, because cadmium has a lower reduction potential, so you can say it has a higher oxidation potential. So cadmium will more likely be oxidized. Now when we write the overall reaction, what we have to do is we have to flip the one that's being oxidized, because here cadmium is shown as being reduced. It's going from a 2 plus down to a 0. So we have to flip it because we've determined that it has to get oxidized. And as we flip it, we can put the two reactions together. So I'm going to just do this in one fell swoop, and what you'll see is that the cadmium, elemental cadmium, will be on the left side, along with tin 2 plus, and then cadmium 2 plus will be on the right side, along with elemental tin. The two electrons actually get cancelled out. And so this is our overall reaction. It's actually quite simple. And to determine the overall cell potential, remember we want to do cathode minus anode. In this case, our cathode is reduction. It's negative 0.136 volts. Our anode is negative 0.403 volts. This would be the same as adding. So we should get ourselves a, take a look what we got. Go ahead, try this in your calculator. 0.267 volts, and this is the voltage of our reaction. Now the voltage of a spontaneous reaction will always be positive. In fact, we'll take a look at this in the subsequent lessons, but if the voltage is positive, which is in this case, that means the reaction will run. So this is a good example to overview the whole thing. I apologize for the little bit of a delay. My book was being sequestered somewhere, but I have fought back, and it is with me here. So this completes lesson 4 of chapter 20.